For decades, we built our defenses around a simple, powerful metaphor, the castle and moat. We constructed a hard, fortified perimeter. We assumed everything inside was trusted, and everything outside was untrusted. This model was intuitive. It was easy to draw on a whiteboard, implemented with firewalls, VPNs, intrusion detection systems. The architectural premise was clear. Control ingress, control egress, and you control security. That model is now architecturally obsolete. It has failed us repeatedly, not because our walls were too weak, but because static binary trust boundaries are a fallacy. The perimeter is a lie. It suggests a clear line between safe and unsafe, but that line has dissolved. Our data is distributed across clouds. Our users work from anywhere on devices we do not always own. Our applications are interconnected systems of microservices and third-party APIs. In this environment, an attacker who bypasses the brittle shell finds a soft, trusting interior. They find a flat network where lateral movement is trivial. The castle and moat model collapses the moment a single phished credential, a vulnerable third-party library, or a misconfigured cloud service provides a foothold. Its fundamental weakness is its binary trust model, which is incapable of containing a threat once it is inside. This discussion deconstructs that failure from an architectural standpoint. We will not be discussing products or reciting marketing slogans. Instead, we will focus on systems, data flows, and decision points that define modern security design. This is for architects, SOC leads, and incident response teams who understand the fundamentals of networking and identity. Our goal is to move beyond the simplistic "identity is the new perimeter" narrative. We will examine why the old model failed so completely and what must replace it at a structural level. The problem was never just about a weak wall. It was about the absence of a security decision system inside the enterprise. We will establish a new architectural thesis grounded in explicit per-request trust evaluation. The solution is not to build higher walls or deeper moats. Rebuilding perimeters is neither practical in a distributed world nor sufficient to stop a determined adversary. The only model that scales and provides genuine resilience is one driven by dynamic decisions, not static defenses. We must shift our focus from blocking traffic at the edge to evaluating trust at the point of access. Every connection, every API call, and every data request must be treated as its own defensible perimeter, subject to its own security policy decision. Our new architecture must be built around a core principle. Trust is not a binary state granted by network location. It is a continuous, dynamic calculation. This discussion will present an architectural framework for achieving this, structured around a clear and logical flow, conceptual flow diagram, signals, policy decision engine, enforcement point. We begin with the collection of signals: identity, device, location, behavior. These signals provide the evidence needed to make an informed decision. Without rich, real-time signals, any policy is merely a guess. The old perimeter model failed for that reason. From signals, we move to the policy engine. The policy engine is the brain of the architecture. It is not a static access control list. It ingests signals. It enriches them with broader context. It computes a risk score or trust level for each access request, deterministic rules, more adaptive models. The policy engine must answer one critical question in real time. Given the available evidence, should this specific request be allowed right now? That decision must be made dynamically for every transaction, without exception. Finally, we arrive at enforcement points. A decision is useless without enforcement. Centralized enforcement at the old network edge is insufficient. Enforcement must be distributed and pushed close to the application, pushed close to the API, pushed close to the data. Inline authorization checks within an application, cryptographic controls at the data layer. Enforcement translates a policy decision into a concrete security outcome, completing the loop from signal to enforcement. Signals, policy, enforcement. This model is the foundation of zero trust. It is a design philosophy, not a product. It replaces a brittle perimeter with resilient, distributed decision and control. Designed for a world where you cannot trust your network. Built to contain breaches by default, making lateral movement costly for attackers. It provides visibility and control for modern SOC and incident response. Our claim: only a decision-driven architecture can provide security at scale. Up next, we dive into signals. 3 parts: the anatomy of a decision, identity signals, device signals. Next, observing intent with behavior and context signals. Finally, the signal integrity problem. A zero-trust architecture is fundamentally a decision system. Any decision is only as good as the information it is based upon. First, inputs into our policy engine. Identity signals. These are more than just a username and password. User credentials, multi-factor authentication, MFA, session tokens, attributes that describe the provenance and state of the principal attempting access. Credential context, long-lived password, a phishing-resistant hardware token, or a federated assertion from a trusted partner. Session lifetime and characteristics matter. Has this identity been authenticated recently? Is it operating under a delegated, narrowly scoped token, or a powerful, persistent credential? Identity signals are observed at the authentication source, such as an IDP, packaged into SAML assertions or JWTs that accompany the request. Parallel stream, device signals. Assuming identity without verifying the endpoint is a critical architectural flaw. Device signals provide evidence about security posture, managed status, patch level, operating system version. More advanced signals involve cryptographic attestation of device state. Can the TPM attest secure boot? Is the firmware state known and untampered? Gathered by agents on endpoints or via MDM and UEM integration. Streamed from collectors at the endpoint as a continuous posture feed. Normalized into a consistent format for the policy engine. The combination of strong identity and device signals forms the baseline for any trust evaluation. Low-risk example: authenticated user plus fully patched corporate managed device with an attested secure boot chain. High-risk example: same user from an unknown personal device with outdated software. The trade-offs here are clear. Collecting rich device signals requires instrumentation, agents, or deep system integration, which can introduce complexity and performance overhead. The latency of these signals is also a factor. Device posture might be checked every few minutes, not every millisecond. Stale posture data could lead the policy engine to make a decision based on outdated information. Define acceptable data freshness thresholds. Architectural design must account for how and where these signals are collected, normalized, and transported. Identity signals are often embedded within authentication and authorization protocols, flowing with the access request. Device signals, conversely, often run on a separate asynchronous channel streaming posture updates to a central repository. The policy engine must correlate these two streams in real time. It queries the device posture repository using an identifier passed with the identity token. This fusion of identity and device telemetry builds a multi-dimensional picture of the access request, moving far beyond a simple binary firewall or VPN check. With a baseline established by identity and device state, we introduce more dynamic signals, behavior, and context. These signals move us from, "What is this entity?" to, "What is it trying to do right now?" Behavioral signals detect deviations from established patterns. Policy engines must ingest telemetry about session activity. Example: a user who normally uses a few apps during business hours suddenly accesses hundreds of files in a sensitive repo at 3 a.m. That's a strong anomalous signal. At the protocol level, an API client starts an unusual sequence of calls or generates a high rate of errors. That could mean a compromised credential or a malfunctioning script. We observe these signals in application logs, API gateway traffic, and network flows. The core challenge: establishing a reliable baseline. That requires learning and observation, profiling normal activity for users, devices, and workloads. Normalization translates raw event logs into anomaly scores or risk flags. For example, web server logs processed by an ML model can flag a session as high risk for anomalous navigation. Behavioral signals have higher latency than identity or device checks because they analyze a window of activity, not a single event. Accuracy is a trade-off. Overly sensitive models create false positives, which cause alert fatigue for SOC teams and friction for users. Context signals add the final enrichment layer, placing requests in an operational setting. Geolocation. Is the login from an unfamiliar country? Time of day? Is the action outside a change window? More advanced context looks at workload relationships. Is this call part of a known business process or an ad hoc dev-to-prod connection? Supply chain provenance, built from a trusted internal registry or pulled from a public repo with no verifiable signature. Context comes from HR databases, user roles, CMDBs, asset info, threat intelligence feeds, malicious IPs, and software bill of materials. They're ingested into the policy engine or an adjacent enrichment tier. Context clarifies ambiguity. A high-risk behavioral alert can be de-escalated if it's a red team exercise. Conversely, a normal request may be flagged if it originates from a workload with a known critical vulnerability. Leveraging context requires a mature data architecture that fuses disparate datasets into a coherent, queryable graph. The signal integrity problem. The entire decision-making framework rests on a foundational assumption: that the signals we receive are trustworthy. A sophisticated adversary will not just try to bypass policy. They will try to subvert the signals themselves. This is the signal integrity problem, and it is a critical architectural consideration. An attacker could attempt to spoof device posture information. An attacker could replay a valid authentication token outside its intended context. An attacker could poison a behavioral baseline by slowly introducing malicious activity over time. Our architecture must be designed assuming signals can be missing, stale, or actively malicious. We cannot blindly trust the data fed into our policy engine. To counter this, we must design for signal verification. For identity, this means token binding to cryptographically tie a bearer token to a specific client device. That prevents token theft and replay. For device signals, rely on hardware-rooted attestation from a TPM, not just a software agent that could be tampered with. Anchor our signals to a hardware root of trust whenever possible. When signals cannot be cryptographically verified, treat them with skepticism and weight them less in risk calculations. The absence of a signal can also be a signal. A device that suddenly stops reporting posture should have its trust decay rapidly. Handling missing or stale data is a key design choice. What does the policy engine do when a device posture check times out? The trade-off: failing open, allow access with degraded visibility, or failing closed, deny access until the signal is restored. Fail closed is more secure, but can impact availability and UX. A common strategy is a tiered response: temporary failure, step-up authentication challenge, or a session with reduced permissions. Prolonged outage for a high-risk user, hard block. Policy must be expressive enough for intermediate actions, not just allow or deny. Ultimately designed for signal integrity by building a resilient, skeptical decision system. Signal collectors at endpoints, gateways, control planes. They are not infallible oracles. They are sensors in a hostile environment. The data they stream to evaluation must be scrutinized. Log the provenance of every signal. Track freshness. Design policies that gracefully degrade when telemetry is unavailable or untrustworthy. This prevents zero trust from collapsing when adversaries try to blind sensors. Instead, the system adapts, treating lack of verified info as a risk signal and adjusting decisions accordingly. From static rules to runtime computation. Once our architecture has collected and verified a rich set of signals, we arrive at the core of the zero trust model, the policy engine. This is where the decision happens. It is crucial to understand that in a zero trust framework, policy is not a static set of access control lists or firewall rules. Those are artifacts of the perimeter-based world, where rules were written once and rarely changed. Instead, zero trust policy is a dynamic runtime computation of risk. The engine's purpose is not to check if an IP address is on an allow list. Its purpose is to calculate whether a specific access request, at a specific moment in time, under a specific set of circumstances, meets the organization's risk appetite. This is a fundamental shift from a static, pre-approved access model to a dynamic, continuously evaluated trust model. This computation transforms discrete signals, identity, device, behavior, context, into a unified decision. The simplest form of this computation uses deterministic rules. For example, if identity is admin and device is managed and context is on-premise, then allow access to production database. While clear and easy to audit, this approach can become brittle and complex at scale, leading to a combinatorial explosion of rules that are difficult to manage. A more sophisticated approach involves creating weighted risk vectors. Each signal is assigned a numerical score based on its inherent risk, and these scores are aggregated. A login from an unmanaged device might add 20 points, an anomalous geographic location adds 30, but a phishing-resistant authenticator subtracts 40. The final score is then compared against predefined thresholds to determine the outcome. More advanced policy engines incorporate Bayesian logic or machine learning models to adjust risk calculations based on observed patterns and historical outcomes. For instance, a model might learn that administrative access from a specific network block, even if it appears anomalous at first, is consistently associated with legitimate maintenance activity and therefore should not trigger a high-risk alert. This allows the system to adapt and reduce false positives over time. The key architectural principle is that the policy engine is not just a rules engine, it is an analytics and computation platform. It must be capable of ingesting diverse data types, executing complex logic, and producing a decision within a strict performance service level agreement to avoid disrupting business operations. Ultimately, the goal is to externalize the authorization decision from the application logic itself. Instead of having hundreds of applications with their own hard-coded access rules, we have a centralized policy decision service that these applications can query. The application asks the policy engine, should this user on this device be allowed to perform this action on this resource? The policy engine performs its risk computation using all available signals and returns a clear, actionable decision, grant, deny, challenge with a step-up authentication. This decouples policy management from the application development lifecycle, allowing security teams to update and refine access logic without requiring code changes or deployments, a critical capability for operating at enterprise scale. The decision pipeline, scoring, and trust semantics. To understand how a policy engine functions in practice, we must trace the flow of a decision through its internal pipeline. Policy decision pipeline flow diagram, request in, signal ingestion and normalization, contextual enrichment, risk score calculation, policy application, decision out, grant, deny, challenge. The process begins when the engine receives an authorization query, typically containing the identity and resource context of the request. The first step is to ingest and normalize the signals associated with this query, retrieving the relevant identity attributes from the security token, fetching the latest device posture from a cache or live query, pulling in recent behavioral analytics data. These disparate signals, arriving in various formats, are transformed into a standardized data structure that the engine's logic can process. This normalization step is critical for ensuring that policy rules can be written in a consistent and abstract manner, independent of the underlying signal sources. With normalized signals in hand, the pipeline moves to the enrichment phase. Here, the engine queries internal and external data sources to add critical context. It might look up the user's role and project assignments from an identity graph. It might fetch the data classification of the target resource from a CMDB. Or it might check the IP address against a real-time threat intelligence feed. This enrichment turns raw data into actionable intelligence. An IP address is just an IP address until enrichment tells us it is part of a known botnet. A device ID is just a string until enrichment tells us the device has a critical vulnerability. This enriched data set forms the complete input for the core risk computation logic. Next, the risk scoring model is applied. Whether it is a deterministic rule set, a weighted vector, or an ML model, this is where the final judgment is made. The output is typically a risk score and a set of attributes that justify that score. This evidence is crucial for logging and auditing. A decision of deny is not useful without the corresponding reason. For example, risk score equals 85. Contributing factor, unmanaged device. Contributing factor, anomalous geo. Contributing factor, sensitive data access. The final step is to apply a decision policy. This policy maps the computed risk score to a concrete outcome. Scores 0 to 25 might result in allow. Scores 26 to 60 might result in allow with an MFA challenge. Scores 61 or higher result in deny. This separation of scoring from decision logic allows for flexible and tiered responses. The final output of this pipeline is not just a simple allow or deny. A mature policy engine produces a transient and scoped trust token. This is a short-lived cryptographic assertion, like a scoped JWT, that grants the bearer specific permissions for a limited time. For example, the token might grant read access to a specific document for the next 5 minutes. The enforcement point can then validate this token without needing to requery the policy engine for every subsequent micro-action. This introduces the concept of continuous trust calculation. Trust is not granted indefinitely but is constantly re-evaluated and reissued in small just-in-time increments, drastically reducing the window of opportunity for an attacker with a compromised session. Scaling policy, distribution, latency, and failure modes. A centralized policy engine that makes every decision for a global enterprise presents an obvious architectural bottleneck and a single point of failure. Therefore, designing a scalable policy evaluation system requires careful consideration of distribution, caching, failure handling. The architectural challenge is to provide low-latency decisions everywhere they are needed, without sacrificing policy consistency. A common pattern to address this is a tiered or hierarchical policy evaluation model. A central policy administration point, or PAP, serves as the source of truth for all policies. Policy decision points, the PDPs, are distributed geographically and logically closer to enforcement points. Enforcement points, the PEPs, sit at the edge where decisions are enforced. Hub and spoke. PAP distributes policies to PDPs, each with a local cache, serving multiple PEPs. To manage latency, these distributed PDPs rely heavily on caching. When a request arrives at an enforcement point, it first checks a local cache for a recent decision, or a valid trust token. A cache hit means the request can be processed immediately. No network call to a remote PDP, essential for performance-sensitive applications. If there is a cache miss, or the cache decision has expired, the enforcement point makes a synchronous call to its nearest PDP. The PDP then executes the full decision pipeline. The results are returned to the enforcement point, and also written back to the cache. The cache's time to live, or TTL, becomes a critical tuning parameter. It balances performance against the risk of acting on stale policy decisions. This distributed architecture raises the question of conflict resolution and consistency. What happens if a policy is updated at the central PAP? The system needs a robust mechanism to propagate that change and invalidate caches across all distributed PDPs. This is often handled through a publish-subscribe messaging bus, or a similar event-driven mechanism. Furthermore, the system must be designed to handle failures gracefully. What happens if a PDP becomes unreachable? The enforcement point must have a clear fail-safe behavior. A fail-closed approach denies access if a decision cannot be obtained, secure, but can hurt availability. A fail-open approach maintains availability, but creates a security blind spot during the outage. A more nuanced strategy configures different fail-safe behaviors based on resource sensitivity. Access to a non-critical internal wiki might fail open, while access to a production database must fail closed. The enforcement point's logic must be able to make this distinction. It must also emit detailed telemetry about its own health and the health of its connection to the PDP. This operational data is vital for the SOC. A sudden spike in fail-open events or PDP connection errors could indicate a system failure, or even an active attack targeting the policy infrastructure itself. Designing resilience and observability into the policy evaluation tier is as important as the policies themselves. Next up, enforcement surfaces. Decoupling enforcement from the perimeter. The policy engine computes a decision, but that decision is purely an abstraction. It has no effect on its own. It must be translated into a concrete action by an enforcement point. In the legacy perimeter model, enforcement was simple and centralized. A firewall or a proxy at the network edge would block or allow traffic based on a static rule. This approach is architecturally insufficient for a zero-trust system. The core reason is a lack of context. An edge firewall operating at layer 4 only sees IP addresses and ports. It has no visibility into the application layer identity, the resource being accessed, or the risk computed by the policy engine. Centralized enforcement at the old perimeter is too far removed from the assets we are protecting to make meaningful, context-aware decisions. Therefore, our architecture must decouple the act of enforcement from the network perimeter and distribute it as close as possible to the protected resource. This principle is known as enforcement locality. Instead of a single choke point at the edge, we create thousands of micro-perimeters throughout the environment. Each application, each API endpoint, each data repository becomes its own policy enforcement point, or PEP. This model ensures that the decision to grant or deny access is enforced directly at the resource itself, just before the access occurs. This eliminates the possibility of an attacker who has gained network access bypassing a distant control and moving laterally within a supposedly trusted zone. Implementing distributed enforcement requires different architectural patterns depending on the context. For modern, cloud-native applications, enforcement logic can be built directly into the application's code or an integrated library. This is the most granular and context-aware form of enforcement, as the application itself has the full context of the user session and the specific action being attempted. For service mesh environments, enforcement is often handled by a sidecar proxy deployed alongside each microservice. The sidecar intercepts all incoming and outgoing traffic, queries the policy engine, and enforces the decision before the request ever reaches the service's business logic, providing a consistent control plane across a heterogeneous service landscape. For legacy applications that cannot be modified, enforcement is typically achieved through an identity-aware proxy or an application access gateway. This component sits in front of the legacy application, intercepts all requests, performs the authentication and authorization dance with the IDP and policy engine, and only forwards legitimate, authorized traffic to the application. While less granular than in-process enforcement, this pattern allows us to wrap a zero-trust control layer around applications that were never designed for it. The key takeaway is that enforcement is not a one-size-fits-all solution. The architecture must support multiple enforcement patterns to provide comprehensive coverage across the entire enterprise estate, from modern microservices to monolithic legacy systems. The three planes of enforcement: application, API, data. To be effective, enforcement must be implemented across three distinct logical planes: the application, the API, and the data itself. Each plane requires different mechanisms and provides a different layer of defense. Application-level enforcement is arguably the most powerful. Here, the PEP is integrated directly into the application runtime. This allows for extremely fine-grained, attribute-based access control. For example, a policy could dictate that a user can view a customer record, but cannot see the credit card number field within that record unless they have performed a step-up authentication. This type of inline authorization and session gating can only be achieved when the enforcement point has deep application context, something a network firewall could never possess. The second plane is API enforcement. In a modern service-oriented architecture, APIs are the connective tissue of the enterprise. Securing them is paramount, Enforcement at this layer is typically handled by API gateways or by sidecar proxies in a service mesh. These PEPs enforce policy on every single API call. A key mechanism here is distributed mutual TLS, MTLS, termination, which ensures that both the client and the server cryptographically prove their identities before any communication occurs. The gateway then validates the incoming token, queries the policy engine, and enforces method-level checks. For example, it might allow a GET request to inventory, but block a POST request from the same service if the policy decision does not explicitly permit it. The final and most fundamental plane is data enforcement. This is the last line of defense, designed to protect data even if application and API controls fail. Enforcement at this layer is tied directly to the data's classification. It involves mechanisms like classification-aware access controls on storage systems, where access is governed by metadata tags on the data itself. Another powerful technique is the use of externalized token exchange for data access. An application does not connect to a database with a long-lived credential. Instead, it presents a short-lived trust token from the policy engine to a broker, which exchanges it for a temporary database session. This ensures that even a compromised application server does not yield persistent credentials to the underlying data stores. These three planes work in concert to create a defense-in-depth model for enforcement. An attacker trying to access sensitive information must bypass controls at the application UI, then find a way to forge a valid token for an API call, and finally, even if they compromise the service itself, they would still need to acquire a just-in-time token to access the underlying data. Each layer of enforcement operates with a different level of context and presents a separate obstacle. Designing an architecture with robust enforcement surfaces on all three planes is what makes lateral movement and data exfiltration so difficult and costly for an adversary within a well-implemented zero-trust environment. Enforcement is not a one-way street. A policy enforcement point does more than just block or allow. It is also a critical sensor that generates vital telemetry. Every enforcement action, every grant, every deny, every challenge must be logged in a structured, detailed format. This telemetry is not just for compliance auditing. It is a rich data stream that provides real-time visibility into who is accessing what and why. This feedback loop is essential for both security operations and the continuous improvement of the policy itself. The logs generated by the PEPs are one of the most valuable sources of data for a modern security operations center. This requires a clear architectural separation between the control plane and the data plane. The data plane is the path of the user's request, services request, where traffic flows and enforcement actions occur. The control plane is the management and orchestration layer where policies are defined and telemetry is collected and analyzed. Enforcement points live on the data plane, but they are managed by and report to the control plane. This separation ensures that even if a data plane component is compromised, it does not compromise administrative functions. The telemetry from all distributed PEPs must be streamed to a central logging and analytics platform, such as a CIEM. The value of this enforcement telemetry is immense. For a SOC analyst, a stream of deny events from a PEPI can be the first indicator of an attack in progress, such as a credential stuffing attempt or a privilege escalation failure. Correlating enforcement logs with signals from the identity and device collectors allows analysts to quickly build a complete picture of an incident. For example, they can see the anomalous behavior that led to a high-risk score, the policy that was triggered, and the specific enforcement point that blocked the malicious action. This fusion of evidence is what enables rapid and precise incident response, moving beyond the noise of disconnected network alerts. Furthermore, this telemetry feeds back into the policy evaluation system itself. By analyzing patterns of access grants and denials, policy administrators can identify rules that are too permissive or too restrictive. For instance, if a specific policy is generating a high volume of false positive denials for a legitimate business process, the telemetry provides the evidence needed to safely refine the rule. This continuous feedback loop, where enforcement emits telemetry, telemetry informs the SOC, and analysis of that telemetry is used to update policy, is what makes a zero-trust architecture an adaptive living system. It is not a static set of defenses, but a dynamic control fabric that learns and hardens over time. The single choke point myth and identity blind spots. A frequent architectural failure in early zero-trust journeys is the subconscious desire to recreate the old perimeter. This manifests as the single choke point myth. Organizations replace the edge firewall with a supposed zero-trust gateway, but they keep routing all traffic through it. The modern proxy may be identity-aware, yet the architecture remains brittle. It becomes a single point of failure and a major performance bottleneck. The design flaw is a failure to embrace distributed enforcement. True zero-trust pushes decision-making and enforcement to the resource edge, not the network edge. Relying on a single gateway ignores service-to-service communication inside a cloud VPC. It fails to contain lateral movement once an attacker gains a foothold in the choke point's blast radius. Another critical failure mode is identity blind spots. Many architectures are built around user-centric identity. They fail to address non-human or shared identities. Identity blind spot, unmanaged service accounts, API keys, machine identities. These often use long-lived, static credentials embedded in code or config files. They represent a massive, often unmonitored attack surface. An attacker who compromises a workload can extract these credentials and move laterally with immense privilege, bypassing user-focused policy controls. A robust architecture treats every identity, human and non-human, as a first-class citizen. It must subject service-to-service communication to the same signal evaluation and policy enforcement as user access, preferably using short-lived, dynamically issued credentials like SPIFFE, SPIRE. Credential sprawl goes beyond service accounts. Developers, administrators, automated systems. They often hold a wide array of standing privileges and access keys. These are frequently stored insecurely, poorly rotated, and inadequately audited. Each long-lived key is a latent risk, a dormant foothold for an attacker. The architectural solution is a shift toward just-in-time access, not just better secrets management. Grant temporary, scoped access in response to an approved, authenticated request. Enforce least privilege dynamically so identities only have permissions for the time they need. The single choke point and identity blind spots are deeply related. Both come from an incomplete zero-trust mental model that clings to perimeter thinking or focuses only on user auth. A successful architecture sees that the threat surface isn't just the edge and identity isn't just users logging in. Every access request, regardless of origin or identity type, is an untrusted event that must be independently verified. Ignore these foundations and you have zero trust in name only, false security, and open avenues for lateral movement. Signal gaps and policy ossification. An architecture's decision quality is entirely dependent on the richness of its signals. A common failure is significant signal gaps creating blind spots. One common gap: lack of device attestation. An organization may invest in identity providers and MFA, but without device posture verification, it solves only half the problem. No endpoint agent, no MDM integration, forces equal treatment of compromised personal laptops and managed endpoints. Missing telemetry creates a hole in risk calculation, collapsing multi-attribute decisions to identity-only checks. Another gap: unmonitored API surface. Adopting microservices and exposing functionality via APIs creates thousands of new entry points. Uninstrumented APIs become blind lanes for attackers. The policy engine lacks visibility into who calls APIs, how they're used, and whether traffic is anomalous. Attackers can use these channels for data exfiltration or command and control. Close the gap with API gateways, service mesh sidecars, generating per-transaction logs, turning API calls into rich signals for policy evaluation. Parallel issue: policy ossification. Policies written as static rules and left untouched become stale. The business changes, new apps deployed, user roles change, and threat intelligence evolves daily. A once appropriate policy can become dangerously permissive. Ossification stems from cumbersome tools and processes, discouraging frequent updates. Result: risk drift. Policy diverges from real security needs. Treat policy as code. Version control, automated testing, CI/CD pipelines. The antidote is continuous evaluation and adaptation. Policy engines should reevaluate long-lived sessions. Morning-granted access can become risky by afternoon. Use mechanisms like continuous access evaluation protocol, receive event-driven signals, high-risk flag, EDR tool, immediately terminate sessions or force reauthentication. Without this, a single trust decision gives attackers hours of opportunity. A dynamic system treats trust as a continuous, revocable lease. Enforcement mismatch and operational friction. One of the most subtle yet critical architectural failures is enforcement mismatch. This occurs when the policy decision is made in a different trust domain or with different context than where the enforcement action takes place. For example, a central policy engine might decide to block access based on rich contextual data, but the enforcement point is a simple Layer 4 firewall that can only block an IP address. Diagram: policy decision point sends complex decision to a simple enforcement point, which translates to block IP, causing collateral damage. This mismatch can lead to collateral damage, where blocking an IP from a shared NAT environment inadvertently denies access to legitimate users. An even worse scenario is when the enforcement point lacks the context to properly implement the decision, effectively failing open or enforcing a weaker version of the intended policy. To prevent this, the architecture must ensure that the policy decision point and policy enforcement point speak the same language. The policies must be written in a way that is natively understood and executable by the enforcement surface. This is why pushing enforcement as close to the resource as possible is so critical. An application-level PEP has the full context of the application session, user attributes, and the resource being requested, allowing it to enforce a fine-grained decision accurately. The design principle is to co-locate decision and enforcement wherever feasible, or at a minimum, to ensure that the decision token passed to the PEP contains all necessary attributes for it to execute the policy faithfully. Finally, perhaps the most common reason zero trust initiatives fail is not technical, but operational. The architecture generates an overwhelming amount of telemetry, but it is not fused or correlated effectively. This creates massive operational friction for the SOC and IR teams. Analysts are flooded with low-confidence alerts from disconnected tools, making it impossible to distinguish real threats from noise. A successful architecture must be designed for consumption by security operations. It must ensure that the signals, policy decisions, and enforcement logs are correlated into a single, coherent narrative for each event. When an alert fires, the analyst should see the user, the device, the anomalous signals, the policy that was violated, and the enforcement action taken, all in one place. This operational integration is not an afterthought. It must be a primary design goal. The architecture must produce evidence, not just alerts. This means structuring logs in a standardized format, enriching them with context at the source, and providing clear identifiers to correlate events across different systems. Without this focus on operational usability, the most technically elegant zero-trust system will fail. It will become a source of friction that security teams begin to tune out or bypass, ultimately eroding the very security it was designed to provide. The ultimate test of a zero-trust architecture is not its ability to block an attack, but its ability to make the detection and response to that attack a fast, precise, and low-friction process for the human operators. From imaginary walls to decision systems. The journey away from perimeter-centric security is not about finding a new perimeter. It is about abandoning static, location-based trust. For decades, we drew an imaginary wall between trusted internal networks and untrusted external ones. That model failed, not because walls were low, but because the assumption was flawed. In a distributed, interconnected enterprise, there is no meaningful inside. The conclusion: stop designing defenses for a network that no longer exists. Shift focus to a resilient, observable, adaptive decision system. Treat trust as a dynamic, per-request calculation. Rethink architectural priorities. Don't ask about firewall rules or network segments. Ask about the flow of decisions. Where do security decisions actually occur? Are they at a distant, context-blind choke point or at the application and data layers? What signals are we using and what signals are we missing? How do we verify telemetry integrity against adversaries trying to blind our sensors? How is policy enforcement instrumented, and how can we guarantee the decision made is the decision enforced? Move beyond static defenses toward dynamic control. Design for operational reality. Does your SOC receive correlated evidence or just a flood of disconnected alerts? When incidents happen, can teams see the chain of events? Compromised identity, anomalous signals, policy evaluation, enforcement action, all in a single, coherent view? An architecture that can't produce clear, actionable evidence under pressure has failed. Operational usability. Empowering analysts to act fast and precisely is the ultimate measure. This is a core design requirement from day one. Rebuild around the architectural core of signals, policy, enforcement. Treat every access request as untrusted and verify it against rich, context-aware policy. Push enforcement to application and data layers. Create thousands of microperimeters instead of one brittle wall. Build systems secure by design, not by accident. The perimeter was a comforting illusion. The future belongs to those who design for reality. Observable, evidence-based decision systems. If you found this helpful, imagine what you'll learn next. Join CyberTechHaus for weekly cybersecurity insights, tools, and breakthroughs. Hit subscribe now and stay ahead of every threat.